Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Right, so this question asks us to do a lot of things with this orbital here. I'm only going to have enough room to do the Lewis structure, so I'll just tell you guys what to do for the VSEPR structure. So for this first molecule, we know that carbon is the central atom, so we can start there. It's got an oxygen and 2 fluorines attached to it. And since that's everything, we know it's a neutral molecule. We know carbon wants 4 bonds, oxygen wants 2, so we put an extra bond here. Now everyone's happy. We need to determine the hybridization of the interior atoms first. So since carbon has 3 things around it, it's going to share those into 3 even orbitals. That's going to be sp2. And the extra p orbital that we didn't blend into this hybridization mix makes that double bond with oxygen. And so if we were to draw this according to valence bond theory, we wouldn't use these right angles here because this is going to be trigonal planar. So these are all going to be 120-degree angles. It's going to fit essentially a triangle. And that will help us answer whether or not this molecule is polar. So we've got polar bonds here. Oxygen and fluorine are all electronegative. And I'm drawing these sort of at angles to indicate that they should be pointing away from each other. And if these were all the same molecule, they would perfectly cancel each other out. But because oxygen and fluorine are going to pull differently, this molecule will be polar. They don't perfectly cancel each other out. So next we have S2Cl2, and this little inscript here tells us that we're going to have a chlorine bonded to a sulfur, bonded to a sulfur, bonded to a chlorine. It's a neutral molecule. Chlorine likes to have 1 bond. Sulfur likes to have, forgot those lone pairs. Sulfur likes to have 2, so everything is happy. They all have the right number of bonds. We need to fill in these lone pairs here. Since sulfur has 6 valence electrons, it uses 2 for bonding. That leaves 4 left over to go into lone pairs. And same with the chlorine. It has 7 electrons, so when it uses 1 to form a bond, it has 6 left over, which is 3 lone pairs. And so everything here has only single bonds in it, which means it's all sp3. But it's not going to be straight linear like this when you draw it, because it needs to be in the hybridization of a tetrahedral. So tetrahedral looks like sort of 2 lines like that, and then a wedge and a dash, sort of like this. And so this molecule is going to be polar because these bonds are going to twist it. They're not going to pull evenly in each direction. These here are polar bonds between the sulfur and the chlorine. And if it was truly linear like this, it wouldn't be polar, but these bonds are, again, not going to be 180 degrees. And finally, we have SF4. So that's sulfur with 4 fluorines around it. And the fluorines are going to have their octets completely filled. Sulfur is going to do one of those rare exceptions where it's breaking the octet rule. That's because it has 6 valence electrons and it's made 4 bonds, which leaves it 2 extra electrons, which have to go somewhere. So now it's got 10 total things around it. So when you break the octet rule, you have to go higher than sp3 in order to fit everything in. So this is sp3, and then it uses a d orbital, sp3d. This is going to form a seesaw type structure. It looks sort of like this in space, where one of these is a bond out, indicated by a wedge, and the other one is a dashed line, indicating that's going back. So this is going to be polar because These bonds here are all polar. And the way that I drew it here in this Lewis structure, they all perfectly cancel each other out. But since they're actually on this seesaw, you see that you'll pull in this direction and in that direction, and that will cancel each other out. But then there's two arrows pulling down this way, and there's no third arrow pulling up to cancel them out. So this will be a polar molecule.